You know that feeling, right? You're nodding along to a coding tutorial, everything clicks, you feel like a total genius. Then, maybe 5 minutes later, you're staring at a blank screen, that blinking cursor, and you can't write a single line of code on your own.
Yeah.
It's that frustrating reality tutorial hell.
Yeah.
You followed every step, typed every single character, and yet, when it's time to fly solo, your brain just goes blank.
It's an incredibly common experience, honestly. And, it's really not your fault.
Right.
What it reveals is, well, a fundamental disconnect, a gap between how we think we learn often, like we're just soaking up information, and how our brains actually acquire complex, usable skills, especially in something like programming.
So our brains are good at recognizing things, but not producing them.
Exactly. Recognizing patterns, yeah, that's easy. But actively producing something totally new from scratch, that requires a very, very different cognitive pathway to be built.
Okay. And that gap, that's precisely what we're diving into today. We're going to explore a really, I think, revolutionary method in programming education, the Pacta CODEX. And get this, what makes this story even more compelling is its first major application. It's being used to transform a Cobol training program. Yes, Cobol.
Yeah. People might raise an eyebrow at that.
Right. A language often dismissed as legacy, but it remains absolutely critical. It's the backbone of countless global systems, financial, governmental, logistics.
It really is. Still running huge parts of the world.
So it's proving that even with a language that presents, let's say, unique challenges, a smarter learning approach can yield, well, pretty astonishing results.
And that's the core of our discussion today. We'll unpack why traditional learning methods so often fall short. We'll dissect the unique origin and the really structured design of the Pacta CODEX method.
Right.
And then we'll zero in on how it's being implemented right now to dramatically transform Cobol learning specifically.
Now, the mission today.
Our mission, is to show you how this method bridges that crucial chasm, the gap between simply knowing about a concept, like the theory, and genuinely knowing how to do it. So you can walk away with skills that actually stick and, importantly, transfer to new situations.
Okay, let's face it. We've all been there, haven't we? We've fallen for the promise. You see the For Dummies books.
Or poorly new, yeah.
Right. Or the Head First series, which look really engaging. And then there are those just endless video courses on platforms like Udemy or YouTube.
So much content out there.
Exactly. And they're all designed to make you feel like you're on this fast track, going to be a coding wizard in no time. But for so many people, they end up leading straight into that tutorial hell we mentioned. It feels productive while you're doing it, but often it's just an illusion.
It absolutely is. And we can break down why. Let's start with that For Dummies approach. It definitely has its initial appeal, right? It's great for demystifying complex topics. It gives you a very clear, linear progression, uses simple analogies, accessible vocabulary. It really excels at breaking down big concepts into these digestible chunks.
Which can definitely lower that initial anxiety, I guess.
Exactly. It reduces what cognitive scientists call intrinsic load, the inherent difficulty of the topic itself, by simplifying things quite a bit. Makes it feel approachable.
So, okay, it's a good way to maybe dip your toes in the water, but it sounds like it doesn't really build lasting capability. Is that fair?
That's precisely the issue. While it lowers the barrier to entry, its core limitation is that it fosters this really strong learner passivity.
Right. You're just reading.
You're essentially a passenger, yeah. You're consuming information rather than actively constructing your own knowledge. The exercises, if there are any, are often few and far between. Immediate feedback is rare. And the concepts, they're frequently presented kind of out of context, disconnected from the kind of real-world projects you'd actually encounter. And critically, it primarily targets your declarative memory, your knowing what?
Knowing the facts.
Knowing the facts, exactly. You might remember the syntax for, say, a Cobol move statement, but you won't intuitively know when and how to effectively integrate that into a larger program structure.
Which leads to that false sense of mastery.
Right. You think you know it, but then when you try to apply it, you hit a wall. And that leads learners to internalize the failure, thinking, I'm just not good at this, when really the method failed them.
Okay, so then you have something like the Head First approach. They really tried to tackle this, didn't they? They called it brain-friendly.
They did, and they incorporated a lot of good cognitive science principles. They use dual encoding, combining text and visuals. Research suggests that can boost memory significantly, sometimes by huge margins compared to text alone.
I like the pictures in those books.
Yeah, they're engaging. And they use the generation effect, where they make you guess answers before explaining them. They build in varied repetitions. The conversational tone is also great for cutting down what's called extrinsic cognitive load.
Okay, what's extrinsic load again?
That's the mental effort you spend just trying to process the instruction itself, like wading through dense text or a confusing layout. Headfirst tries to minimize that, so your brain isn't getting bogged down just trying to understand how it's being taught.
And the humor and metaphors.
That's about emotional engagement. Hooking into the limbic system can make concepts more memorable. So yes, Headfirst definitely makes an effort to engage your brain differently, optimizing how you acquire that declarative knowledge.
A but. There's a but coming, I feel.
There's a but. Even with all its cleverness, a Headfirst book is still fundamentally a static medium. A book.
Right. It can't react.
Exactly. Those engaging, scripted scenarios, while really illustrative, they simply cannot substitute for sustained, deliberate practice. Practice that's coupled with the kind of fine-grained, immediate correction that's absolutely essential for actually building a skill.
Okay.
The exercises it offers, they aren't typically linked to robust skill frameworks or, crucially, automated testing. A book, just by its nature, cannot provide the interactive, real-time feedback your brain needs to truly hardwire a skill like coding. It prepares you beautifully for procedural learning, but it can't fully deliver on it.
Which brings us to the behemoth video tutorials.
Yeah.
MOSCs, YouTube, Udemy. These platforms are just everywhere now,
Yeah.
incredibly accessible.
Hugely accessible.
You get clear demonstrations, right? You can see exactly what the expert is typing. And that just-in-time learning. You hit a specific problem, you search, you find a video. Feels very efficient.
Mm-hmm. And it can even activate what are called mirror neurons. Watching someone else code skillfully gives you this initial but often quite deceptive sense of doing it yourself.
Ah, so you feel like you're learning by watching.
Precisely. It feels incredibly productive, like you're absorbing everything just by observation. But this is where that illusion of competence we talked about truly reaches its peak.
Why? What's happening there?
Watching an expert code primarily activates recognition. You understand what's being shown on the screen, but it conspicuously bypasses active recall.
Active recall.
That's the much harder yet absolutely essential process of producing that code from your own memory without looking at notes or the video. That's the real work of learning.
So watching is passive.
It leads to passive consumption, yes, and often just replication typing what you see without genuine problem solving. These videos often lack what's called active recovery. You're rarely prompted to pause and try to recall information without notes.
Okay.
There's also usually a shortage of interleaving. That's practicing different types of problems in a mixed-up order, which is crucial for making skills flexible and transferable. Instead, you often just practice one thing over and over in isolation.
And feedback.
Individualized formative assessment is minimal. Authentic debugging practice or peer code review, practically non-existent in most video tutorials. And, well, let's be honest about the economics. The business models of many of these platforms can inadvertently incentivize courses that feel frictionless and easy to consume. They want high completion rates, right?
Yeah.
Which sometimes prioritizes making it feel easy over making it genuinely challenging and effective for deep learning.
So, okay, if we strip it all down, try to get to the core problem, it's that our brains trick us. We confuse recognizing something with being able to actually produce it.
That's the crux of it. It's like watching a brilliant pianist play a concerto. You can follow the notes, understand the rhythm, appreciate the artistry, maybe even nod along.
Sure.
But that doesn't mean you can suddenly sit down at the piano and play it yourself. Not even close.
Right.
Programming, and especially a language like Cobol with its very precise structure and logic, absolutely demands procedural memory, the actual knowing how to do it, not just memorizing declarative facts. It's about building those deep, robust neural pathways for action, not just for observation. Hashtag 1.2, the neurocognitive roots of learning failure.
Okay, so we've established this fundamental problem, the illusion of competence. Given that, what exactly is happening inside our brains that causes these seemingly helpful resources, the books, the videos, to fall short so often? Where does the science of learning tell us we're actually going wrong?
Well, it primarily comes down to this really critical divide between two distinct memory systems in the human brain.
Two systems.
Yep. First, we have declarative memory. You can think of this as your knowing what system.
Okay.
This system stores explicit knowledge, facts, concepts, rules, things you can consciously recall and verbalize. So remembering the specific Cobol keywords for the data division or the definition of how a perform until loop works, that's declarative memory doing its job.
Like textbook knowledge.
Exactly like textbook knowledge. This information is processed and stored in regions like the hippocampus. And as we just discussed, traditional learning tools like books and videos, they are actually very, very good at delivering this kind of information.
Okay, so that's knowing what, and then there's the other type, the one you called knowing how.
Precisely. That's procedural memory. This system is different. It stores implicit knowledge, skills, and habits, things acquired through repetition and practice.
Like riding a bike.
Exactly like riding a bike or tying your shoes. It becomes automated, allowing you to perform actions largely without conscious effort. In Cobol terms, this isn't just knowing the syntax, it's intuitively structuring a complex file processing routine or systematically debugging an accept display error without having to think through every single step, or writing clean, idiomatic Cobol code that other developers can easily understand.
So it's more instinctual almost.
It becomes that way through practice, yes. This memory is encoded in different brain structures, like the basal ganglia and the cerebellum. It's fluid, it becomes automatic, and it's absolutely foundational for true expertise in any skill, including programming.
So the million-dollar question then is, how do we convert one into the other? How do we take that knowing what from the books and videos and turn it into actual usable knowing how?
That's the conversion challenge. And that's precisely where most traditional methods completely fall flat.
They don't bridge the gap.
They don't bridge the gap. There's a well-known cognitive model, John Anderson's ACTR model, that describes this transformation in roughly 3 stages.
Okay.
First, you have the cognitive stage. This is where your declarative knowledge, the facts you just learned, guides your actions. It's slow, it's very error-prone. You're consciously thinking about every single line of Cobol code you write.
Sounds familiar.
Right. Then, with practice, you move to the associative stage. Here, those declarative rules start getting compiled, bundled together into more efficient, interconnected procedures. Things start to flow a bit better. Getting smoother. And finally, you reach the autonomous stage. This is where the skill becomes highly automated, almost subconscious. You can just do it. Most traditional resources, unfortunately, only really support that very first cognitive stage.
So they leave you stuck.
They leave you stuck, unable to effectively bridge the gap to fluid, autonomous coding. It's like they hand you a really detailed recipe book, but then expect you to become a gourmet chef without ever letting you step into a real kitchen and practice.
That makes sense.
Yeah.
And this ties directly into cognitive load theory,
Yep.
right? John Sweller's work. You mentioned intrinsic load earlier, but there are 2 other types that are really important here.
That's absolutely right. So we have intrinsic load, that's the inherent complexity of the programming concept itself, like understanding, say, how table handling works in Cobol. That difficulty is unavoidable, it's part of the topic. Then there's extrinsic load. This is the mental effort required just to process the instructional material itself. And crucially, this effort does not contribute to actual learning.
Like struggling with a bad explanation.
Exactly. Or trying to keep pace with a super fast-talking video instructor, or wrestling with multiple open windows on your screen, or constantly having to pause and rewind because the presentation itself is just poorly designed or confusing. Passive methods, especially poorly designed ones, often inadvertently maximize this unproductive load.
So if I'm spending all my brain power just trying to follow along with the video or the confusing book.
Then you don't have enough mental bandwidth left over for the actual learning.
Okay.
And that brings us to the third type, germane load. This is the good stuff. This is the desirable mental effort that's actually dedicated to deep processing, to building those robust mental models, cognitive scientists call them schemas, and transferring them effectively into your long-term memory.
And passive methods.
The terrible irony is, passive methods often minimize this critical germane load. Learners end up exhausting their limited cognitive resources just processing the presentation format, leaving very little mental bandwidth for the deep, effortful work of true understanding and genuine skill development.
It's like the instructor in the video is doing all the thinking for you.
Precisely. Video tutorials often completely invert the learning dynamic. The instructor performs the essential cognitive work demonstrating their thought process, their problem-solving steps, while the learner is often reduced to just passively transcribing or simply recognizing what's happening on screen.
Okay, so cognitive load is a huge factor. Beyond that, what else holds us back in these traditional approaches?
Another absolutely critical missing piece is the lack of immediate specific feedback. Programming is what you might call an error-dense domain.
Meaning you make a lot of mistakes.
You will make mistakes. It's unavoidable. It's part of the process. But without feedback within a really crucial window, typically around 200 to 500 milliseconds, that fast. Whether that feedback comes from a compiler telling you there's a syntax error, or from automated tests failing, or even from a human reviewer pointing something out. Without that quick feedback, learners very quickly start to stabilize bad habits and reinforce incorrect understandings.
And fixing those later is much harder.
Much, much harder. It's often actually worse than having no knowledge at all, because now you have to unlearn the wrong way before you can learn the right way.
So without quick correction, we're basically just practicing our mistakes over and over.
That's a great way to put it. We also often see an absence of desirable difficulty. Optimal learning doesn't actually happen when things are too easy.
Right, you need a bit of challenge.
You need to grapple a bit. Learning occurs most effectively when tasks are slightly challenging, forcing effort and focus. Linear videos, by trying to smooth over every potential obstacle, and often not requiring active recall or application in varied contexts, prevent the brain from building those robust, flexible, transferable skills. The brain needs those desirable difficulties, those little bumps in the road, to truly internalize a concept deeply.
And finally, you mentioned something about metacognitive tooling. That sounds important. It's not just about learning what to do.
It's about learning how to learn, and crucially, how to improve. Absolutely. Learners don't just magically develop critical self-assessment skills. Things like keeping a systematic bug journal, using quality checklists for their code, or being able to effectively evaluate their own Cobol programs for clarity and efficiency.
You need to be taught how to do that.
You need explicit tools and explicit training in how to use them. Without these metacognitive strategies, learners remain perpetually dependent on external instruction. They don't become autonomous, self-correcting learners, which is absolutely essential for navigating the complexities of real-world software development, especially in a domain like Cobol maintenance.
Okay, so we've really painted a picture here of the widespread frustrations and the deep cognitive issues that are just baked into a lot of traditional programming education. It's clear there's a massive problem space here.
Absolutely.
And this leads us directly to one individual, Alain STEVENS. He's a seasoned IT consultant who looked at all this and decided, okay, we need to completely rethink how we teach programming. And his personal journey, interestingly, perfectly illustrates the very problem he set out to solve.
STEVENs' background is absolutely pivotal to understanding where the Pacta CODEX came from. He has over 25 years, maybe more now, as an IT consultant. So he was absolutely no stranger to the tutorial hell phenomenon we've been talking about.
He lived it himself.
He lived it himself. Just like so many others, he'd consumed countless books, countless online courses, YouTube, LinkedIn Learning, Udemy, you name it. And he found himself stuck in that same familiar loop. Understanding the theory, grasping the concepts while watching or reading, but then struggling significantly when it came to autonomous application, actually building something from scratch. He came to the conclusion that these resources, despite their promises, simply weren't designed for solid, practical, and truly memorable learning that actually sticks.
Here's where his story takes a really interesting turn, right? His breakthrough inspiration didn't come from another coding book or a different online course. It came from a seemingly completely unrelated publishing.
That's the unique and fascinating twist. Back in the 2000s, STEVENS actually co-founded a publishing house called Pacta Edition.
Pacta Editions, okay.
And they specialized in producing extremely complex, multilingual legal works, particularly things like international business law contracts and agreements.
Wow, okay. Complex stuff.
Incredibly complex. But these weren't just static reference books. They were designed as powerful knowledge management tools. They meticulously structured these intricate legal concepts into modular, reusable elements.
Modular. Like building blocks.
Exactly like building blocks. This allowed legal professionals to effectively compose sophisticated, highly customized contracts by assembling these predefined, well-structured elements. The entire experience, the entire system, was fundamentally about transforming dense, complex, declarative knowledge, the legal text itself, into actionable procedural competence.
The skill of actually drafting an effective contract.
Precisely, the skill of effective contract drafting.
So he saw this direct parallel, taking really complex, abstract information and designing a system to turn it into a concrete, usable, real-world skill.
That was the insight. He realized that this methodology, this structured decomposition, this focus on precise application, this iterative refinement used to engineer legal knowledge for actionable outcomes could be directly transposed to the world of IT education.
Interesting.
He understood, maybe because of that unique background, that effective learning isn't just about absorbing information passively. It's fundamentally about designing a system that deliberately, actively transforms knowing what into knowing how to do. His legal publishing background gave him this unique lens, this system design perspective, that was largely missing in traditional programming education. He saw how to build a structure where information wasn't just stored, but made profoundly actionable.
Okay, so building on that really unique insight from legal publishing, Alain STEVENS developed this structured, neurocompatible, and highly actionable method, the Pacta CODEX. And you called it an anti-tutorial approach earlier, which I love. It sounds like it's designed to actively combat all those pitfalls we just spent time detailing.
That's the perfect way to frame it, yeah. The Pacta Codex is fundamentally a short, repetitive learning cycle. It's engineered, really, to actively build expertise step by step. It makes that crucial shift, moving learners away from just a passive consumption towards active creation and problem solving.
And it's built on solid science.
Absolutely. It's built on a bedrock of proven neuropedagogical principles. Things we know work for learning. Spaced repetition to fight forgetting, interleaving to build flexibility, introducing desirable difficulties to deepen understanding, using dual coding, text and visuals, carefully managing cognitive load, aiming for mastery learning before moving on, and incorporating elements of cognitive apprenticeship where learners see thinking made visible.
Wow, okay. That's a lot packed in.
It is, and each of its 5 steps is meticulously crafted. It's designed to directly address a specific cognitive challenge that typically hinders learning complex skills like Cobol programming.
All right, let's break down these 5 steps then. It's an acronym, right? CODEX. Conceptualize, operate, debug, explain, and explore.
That's it.
Okay, starting with C for conceptualize, or conceptualizer in French. This is where an idea, a concept, or maybe a command is introduced, but how is it done differently?
The key here is minimalism and clarity. The primary purpose of Conceptualize is to deliver that pure, efficient, declarative knowledge, the what, but with minimal cognitive overhead. So these are microcapsules, typically just 5 to 8 minutes long, very focused.
Short and sweet.
Short and sweet. They employ visual aids like clear schemas or diagrams, and crucially minimal examples. Just enough code to illustrate the core idea, nothing more. This drastically reduces that extrinsic cognitive load we talked about.
So your brain isn't wrestling with complexity, just the core concept.
Exactly. It allows your brain to focus entirely on grasping the fundamental concept, building a solid initial mental anchor. It uses techniques like worked examples showing a complete solution first, followed by fading, where parts are gradually removed for you to fill in. And it incorporates things like concept cards for key syntax or patterns, designed to work with spaced repetition systems to ensure that initial memorization actually happens. This is where you firmly grasp the what.
Okay, makes sense. Then immediately after that, it's O for operate, or operer. This is where you actually put that concept into practice by writing executable code, aiming for a specific, precise objective.
Yes, and this is a critical pivot point in the cycle. Operate is the very first direct step in that crucial conversion process, turning your declarative knowing what into actual procedural competence, the knowing how.
Getting your hands dirty.
Getting your hands dirty immediately. This immediate targeted action happens within a guided, safe environment. Think of a coded sandbox, maybe right in the browser, that comes equipped with instant unit tests.
So you know right away if your code works.
Instantly. You're aiming for clear, measurable metrics, passing all the provided tests, maybe adhering to specific code readability standards, or sometimes optimizing for performance or complexity. This step vigorously engages your procedural memory through direct active doing. It makes that abstract concept you just learned concrete and actionable right away.
Okay, concept learned, code written. Then comes D for debug, or debugger. And this isn't just fixing your own typos. It's actively learning to identify and correct typical errors and really understand those compiler messages.
Yes. Debug elevates debugging from being this frustrating, often demoralizing obstacle into a central teachable skill in itself. It's treated as core competency, not an afterthought.
How do you teach debugging?
Well, learners are deliberately exposed to what we call bug seeds. These are common, typical errors that are intentionally planted within the exercises.
You put bugs in on purpose?
On purpose. And then you're equipped with tools like an error journal. This guides you through a systematic problem-solving process. You document the symptom, what went wrong, then your hypotheses, what might be causing it, then the tests you run to check those hypotheses, then the actual fix, and finally the lesson learned so you don't make the same mistake again.
That sounds really structured.
It trains resilience, analytical thinking, and effective diagnostic skills. The platform also includes things like intuitive linters tools that check code style and potential issues, and guided compiler messages that offer progressive hints. Instead of just a cryptic error code, it might give you clue 1, then clue 2, gradually leading you towards understanding and fixing the problem yourself. This is absolutely crucial for mastering languages like Cobol, where error messages can sometimes be quite dense or historical.
Right, okay. So you've conceptualized, you've operated, you've debugged. Now comes E for explain or explicker. This is where you have to reformulate the concept in your own words, maybe write a justification for your code, or even teach it to a peer. Why this step?
This metacognition step is incredibly powerful for consolidating learning. It forces deep processing of the information you've just worked with. It's inspired by the renowned Feynman technique.
The idea that you don't truly understand something until you can explain it simply.
Exactly. Requiring you to verbalize or write a justification for why your solution works, why it passes the test, why it's designed that way. That is the ultimate test of true understanding. It solidifies your mental model and pushes you far beyond just passively recognizing the concept towards actively mastering it.
So it forces you to articulate your thinking.
Precisely. This might involve specific Feynman prompts within the platform, like asking you to explain in 5 hate lines why your Cobol solution handles edge cases correctly, or maybe engaging in short, structured peer reviews using clear rubrics where you evaluate a peer's code or have yours evaluated. It's the moment you truly own the knowledge internally.
Okay, one step left. X for explore or explorer. Here you apply the notion you've just mastered, but in new contexts. You vary the situations, maybe work on mini projects. What's the goal here?
Explore directly tackles that dreaded page blank syndrome, staring at a blank screen when faced with a new problem. Its core purpose is to guarantee the transferability of skills.
Making sure you can use it elsewhere.
Exactly. By applying the learned Cobol concepts in varied scenarios, in different mini projects, typically maybe 90 to 120 minutes long, that come with realistic constraints.
Like what kind of constraints?
Things like optimizing for performance, which is critical on mainframes, handling different types of file I/O operations, formatting complex reports according to specific business rules, dealing with tricky data validation. By doing this, you build flexible, robust mental schemas.
Schemas. Those mental models again.
Those mental models, yes. But now they're more adaptable. They can be applied and modified to tackle novel, real-world problems that you haven't seen before. This ensures your learning isn't brittle, isn't confined only to the exact examples you saw in a tutorial. It prepares you for the dynamic, often unpredictable nature of maintaining large, evolving Cobol systems in the real world.
Wow. Okay, so if I'm getting this right, each step in this codex cycle isn't just like another task on a checklist. It's specifically designed to target and actively resolve one of those cognitive limitations we identified earlier in traditional learning methods.
That's absolutely the intention. It's truly an engineering approach to building expertise, rather than just presenting information and hoping learners will magically figure out how to apply it effectively.
Yeah, it sounds much more deliberate, from minimizing that cognitive load right at the start in Conceptualize to forcing that active recall and deep processing in Explain, and then really building that real-world application muscle in Explore.
Yeah.
It feels like a direct design for making you not just learn something, but truly master it.
That's the goal, deliberate design for mastery.
Now, I have to come back to this because for many of our listeners, the mention of Cobol might still conjure up images of, I don't know, dusty mainframes, green screens, maybe a programming language from a bygone era.
It has that reputation for some, yes.
So some might still be thinking, Cobol? Really? Why apply such a cutting-edge, neuro-based learning methodology to a language often just labeled as legacy?
It's a really great question, and the answer, I think, truly underscores the power and the necessity of the Codex method. Cobol, far from being obsolete, remains absolutely critical. It underpins a vast amount of the world's essential infrastructure. We're talking finance, government services, insurance, logistics, retail. Huge sectors rely on it.
Still running the show behind the scenes.
Still running the show. And because of its history and structure, Cobol actually presents some unique cognitive demands that make it a perfect proving ground for a method like Codex. Its inherent challenges force a level of clarity and structured practice that might not seem as immediately critical in newer, perhaps more forgiving languages, but are essential for robust learning everywhere. Cobol highlights exactly why the Codex principles are so effective.
Okay, can you give us an example? What are some of those specific challenges in Cobol that Codex addresses head-on?
Certainly. One major, immediately obvious challenge is Cobol's inherent verbosity.
It's wordy, very English-like.
Very wordy, very structured, all those divisions, sections, move corresponding. This wordiness and the strict hierarchical structure can easily overload a beginner's working memory. It's just a lot to keep track of initially.
Right.
So the Codex Conceptualize step directly tackles this. It uses those visual schemas we mentioned to clarify the program's logic flow, breaking down the verbose structures into smaller, more manageable microelements. We might even use spatial layouts and diagrams to help learners mentally navigate the different divisions and paragraphs of a complex Cobol program, making it feel less like an overwhelming wall of text.
Okay, so it's about simplifying that initial mental burden, making the complex feel more accessible. What other way Cobol actually forces you to think? It's not like Python or Java, is it?
Not at all. That's another key point. Cobol often requires adopting a very specific procedural thinking paradigm. It's less object-oriented, more focused on sequential processing, data structures defined up front, flow of control. This can be a significant mental shift, especially for developers coming from modern, object-oriented languages.
A different way of problem solving.
A fundamentally different way. Codex addresses this shift directly through that immediate targeted practice in the operate step and providing context and Conceptualize. We often include a bit of historical context explaining why Cobol is structured the way it is, relating it to the hardware constraints of the time, for instance. And we draw analogies to modern concepts where possible to help bridge those conceptual gaps and make its distinct logic click for learners from different backgrounds.
And what about the actual job most Cobol programmers do?
That's critical. A massive part of professional Cobol work today involves maintaining existing, often incredibly large and complex, legacy code bases. Code that might be decades old.
Not just writing new stuff.
Often, primarily not writing new stuff, but understanding, modifying, and debugging existing systems. The debug and explore steps in Codex are specifically designed to prepare learners for this reality. They don't just learn syntax, they learn how to systematically analyze failing code, how to understand typical Cobol runtime errors or JCL issues, how to adapt solutions to work within the constraints of varied mainframe architectures and operating systems. This practical focus on maintenance is invaluable.
So it sounds like Cobol, far from being just some dusty old relic, is actually this highly relevant, challenging language where applying the right learning method, one designed for its specific cognitive demands, can make a truly profound difference. Codex seems perfectly suited for it.
It really is. The challenges inherent in Cobol make the benefits of a structured, neurocompatible approach like Codex incredibly clear and impactful.
Okay, so we understand the Codex philosophy, the CODEX cycle. How does this translate into a real-world learning environment? You mentioned Pacta Learning's Cobol training program is the first concrete embodiment of this whole anti-tutorial approach. What does that actually look like? What's the platform like?
Indeed, the platform isn't just, a collection of videos and quizzes slapped together. It's designed as a deeply integrated ecosystem built from the ground up to actively support every single step of the Codex method and really optimize the entire learning process based on cognitive science.
So it's more than just content delivery.
Much more. We start with the fundamentals, ensuring access and minimizing unnecessary cognitive load. That means robust, multilingual adaptability and cognitive accessibility.
Multilingual. How does that work?
All the pedagogical content, the explanations, the instructions, the prompts can be instantly translated right within the browser interface. This completely eliminates linguistic barriers for international teams or learners whose first language isn't, say, English or French. We also culturally adapt examples, things like date formats, currency symbols, local business conventions to make them relevant globally, and there's an integrated multilingual technical glossary for quick lookups.
That sounds incredibly useful for global organizations. And cognitive accessibility.
That's about catering to different learning needs and preferences. We have intelligent, voice-reading, high-quality text-to-speech that's specifically optimized for reading code aloud accurately. There's adaptive reading speed control, which can even automatically slow down when covering particularly complex Cobol concepts. And it incorporates contextual pauses, allowing time for reflection, plus on-demand repetition of difficult passages. The core goal here is to ensure every learner's precious cognitive energy is spent on mastering Cobol itself, not on battling the interface or struggling with the presentation format.
That's a powerful foundation. Ensuring that initial conceptualized step is truly effective for literally everyone, regardless of language or learning style. Okay, so access is covered. How does the platform then handle the really active parts, the operate and debug steps?
Right, getting hands-on. Critical for memory consolidation and keeping learners actively engaged, the platform deeply integrates microlearning and spaced repetition.
Microlearn, those short modules again.
Exactly. Modules are meticulously designed to be short, respecting those natural attention cycles, typically 7 to 12 minutes maximum per core concept. Each has a single, clear objective to prevent cognitive dispersion. You're focused on one thing at a time.
And the spaced repetition, how's that integrated?
There's an integrated spaced repetition system, SRS, functioning much like popular tools like Anki. It automatically generates personalized flashcards based on the concepts you're learning and, importantly, based on the specific errors you make in exercises.
Oh, so it learns from your mistakes.
It learns from your mistakes to help you reinforce the right patterns. It then automatically plans the optimal review intervals for you, based on established models of the human forgetting curve. Think reviewing a tricky concept or syntax rule at J+1, one day later, then J+3, J+7, J+15, and so on, tailored to your individual performance.
So it's actively fighting that forgetting curve for you right when you need it. Okay, and for the actual hands-on coding, where does that happen?
That's where the Integrated Interactive Development Environment, IDE, comes in. This isn't a separate piece of software you have to install. It's a fully functional sandbox environment running right in your browser, embedded directly within the learning modules.
So no setup hassles.
Minimal setup hassles. It comes complete with instant executable unit tests that run against your Cobol code, linters configured for Cobol best practices and common pitfalls, and automatic code formatters to ensure consistency.
That instant feedback from tests must be huge, especially with Cobol's strict syntax.
Absolutely transformative. Knowing immediately if your perform loop is off by one or if your data division structure is invalid makes a massive difference compared to waiting minutes for a batch compile on a traditional system. The IDE also features intelligent auto-completion relevant to Cobol syntax, and even if your device supports it, can provide subtle haptic feedback.
Haptic feedback, like a vibration.
Exactly. A gentle vibration on common errors, providing another immediate non-visual cue that something needs attention. It's another way to reduce cognitive load by providing instant signals.
Wow. Okay, and what kind of exercises do you actually do in this IDE?
We use a wide variety to ensure comprehensive skill development and prevent learners from just memorizing solutions to one type of problem. There are completion problems, where maybe 30–60% of the Cobol code is missing and you have to fill in the blanks logically. There are parsons problems, where lines or blocks of Cobol code are scrambled and you have to drag and drop them in the correct logical order, great for understanding structure.
That sounds challenging.
It really makes you think about flow. Then there are bug hunt exercises, where you're given a piece of Cobol code that has known bugs, and your job is to find and correct them using the debugger and your analytical skills. And finally, timed katas, small focused coding challenges designed to build fluidity, speed, and automaticity with common Cobol patterns. This variety prevents rote learning and fosters true adaptability.
And for the debug steps specifically, you mentioned those bug seeds earlier. How does the platform support actually learning from those deliberately planted errors?
Our enhanced debugging and error management system is really core to the method. Those bug seeds, typical common Cobol errors like data type mismatches, incorrect loop boundaries, mishandling end-of-file conditions, are deliberately programmed into specific exercises.
To force you to confront them.
To force you to confront them in a safe environment. Learners are then guided through the diagnosis process using that journaled error or error journal tool we talked about. It prompts them systematically. What's the symptom? What are your hypotheses? What tests will you run? What was the fix? What's the lesson?
Building that systematic approach.
Exactly. The built-in linters and the guided compiler messages also play a huge role here, offering those progressive hints. Clue 1, clue 2. Maybe look at this variable. Okay, here's the solution explanation. Rather than just spitting out an often cryptic mainframe error code, we even gamify the debugging progression slightly, rewarding successful bug hunts to keep motivation high.
That really sounds like it transforms debugging from this source of immense frustration into a core learnable skill. Okay, what about the last two steps of Codex, explain and explore? The metacognition and the real-world application. How does the platform support those?
Great question. For metacognition and pure learning, the explain part, we rely heavily on those find-in prompts. The platform will explicitly ask learners, after they've successfully completed an exercise, to explain in 5 date lines why your Cobol solution correctly handles the specified file locking mechanism, for example. This forces them to articulate their understanding.
Making them justify their code.
Precisely. We also facilitate short, guided peer reviews. These use clear rubrics focusing on key quality aspects like good Cobol naming conventions, code decoupling modularity, appropriate use of comments, and effective testing strategies. Interestingly, this can sometimes involve an empathic AI partner.
An AI for code review.
Yes, an AI that can play the role of either a beginner asking clarifying questions, I don't understand this part, or an expert challenging assumptions, have you considered this edge case, prompting deeper reflection from the learner. We also build in regular retrieval practice, maybe 3 quick multiple-choice questions done without notes at the end of each learning block to reinforce recall. Plus, there are things like quality checklists, bronze, silver, bold standards for naming, keeping procedures short, test coverage, cyclomatic complexity, and a personal logbook for metacognition where learners jot down what I tried, what I learned, what I still need to review.
And a dashboard to see progress.
Absolutely. A personal dashboard tracks key metrics like time spent on task, test pass rates, the diversity of exercises completed, and how often concepts are being revisited through spaced repetition. This fosters self-awareness and helps learners see their own progress.
That's incredibly comprehensive for building understanding and self-awareness. Now, how do you ensure all these skills actually transfer to the messy reality of real-world Cobol projects? The explore step.
That's where our focus on robust project-based learning and transfer kicks in. The entire curriculum is structured using a spiral learning approach.
Spiral learning.
Meaning concepts aren't just taught once and then dropped. They're revisited multiple times, each time at an increasing level of complexity and integrated into more authentic, larger projects. Learners start with those focused exercises, then move on to mini projects. These are typically 90, 120 minutes long and involve applying multiple concepts together under realistic constraints.
Like the performance or file I/O constraints you mentioned.
Exactly. Optimizing for mainframe CPU cycles, handling specific vSAM file operations, generating complex reports according to detailed specifications, implementing robust error handling and recovery routines. These mini projects build confidence and integration skills.
And then bigger projects.
Then it progresses to larger capstone projects. These come with much more detailed briefs mimicking real-world specifications, including comprehensive test data sets, specific performance targets that must be met, requirements for logging and auditing. These really simulate the demands of a professional Cobol development task.
And you vary the context, too.
Critically, yes. Exercises explicitly include context variation. You might solve a problem using one approach, then be asked to solve the same problem but with different input data, or using a different Cobol feature, or perhaps without relying on a specific utility program. We also include transfer questions like, imagine the standard sorting utility wasn't available on this system. How would you approach sorting this large data set using only core Cobol features? This constantly pushes learners to think flexibly and adapt their knowledge.
That sounds exhausting but effective.
Yeah.
And for those moments when you get really slick, even with all this structure, you've even got an AI mentor built in, don't you?
We do. To provide that just-in-time support without just giving away the answer, we have a Socratic AI mentor. Some call it Dr. Debug. It's inspired by research concepts like neurocode.
Socratic, meaning it asks questions.
Exactly. It guides the learner's problem-solving process by asking probing questions rather than directly providing solutions. It might ask, okay, walk me through your understanding of what this specific Cobol paragraph is supposed to accomplish. Or can you break down this complex batch update problem into smaller, more manageable steps? Or what assumptions are you making about the input data here?
So it forces the learner to do the thinking.
It forces the learner to perform the essential cognitive work themselves, to articulate their reasoning, identify their own misconceptions just as a skilled human tutor would. It leads them towards their own solutions, building true problem-solving capacity.
That is truly an end-to-end ecosystem. It's hard to grasp just how different that is from a simple video tutorial. To make it even more tangible for our listeners, could you maybe walk us through a typical 90-minute or 2-hour Codex module? Let's stick with Cobol, maybe one focus on something fundamental, like loops and iterations.
Absolutely. A typical 90 to 120-minute module on, say, Cobol loops, perform statements, might look something like this. See, Conceptualize around 7 minutes. We'd introduce the basic concepts of iteration using perform varying and perform until. This would include a clear flow diagram visually showing the loop structure and condition checking, alongside a minimal code example just showing the core syntax. Operate around 25 minutes. Immediately pivot to the IDE for maybe 3 distinct targeted coding tasks. Task 1 might be completing a simple loop to process array elements. Task 2 could involve writing a loop with a more complex termination condition. Task 3 might require nested loops. All with visible unit tests providing instant feedback and tiered hints available if the learner gets stuck. Debug around 15 minutes. Now tackle 2 pre-planted bug seeds related to loops. Perhaps one exercise has a classic off-by-1 error in the loop counter, perform varying. Another might have a bug where a variable controlling the loop condition is incorrectly modified inside the loop, causing an infinite loop. The learner uses the debugger and the error journal to find and fix these. Explain around 10 minutes. After successfully debugging, the learner gets a Feynman prompt, something like, in 5 of 8 lines, explain your choice of loop invariance, conditions that must always be true, and the specific termination conditions you used in task 2. Why are they correct? Explore, around 30-45 minutes. Finally, apply this loop knowledge in a slightly new context. Maybe refactor the iterative solution from task 3 into a different structure, or apply the looping logic to process records from a sequential input file until end of file, handling potential I/O errors. This might involve dealing with slightly different data structures or performance considerations. Spaced repetition, ongoing, maybe 3 minutes integrated or prompted later, and woven throughout or prompted later by the SRS would be maybe 5 quick multiple choice questions hitting key concepts, syntax reminders, common loop errors, differences between perform varying and until sent automatically at those optimal intervals, J+1, J+4, J+10, etc., based on their previous performance.
Wow.
That's remote.
Yeah, that's a completely integrated dynamic cycle. Much more active and demanding than just watching someone else code a loop. Hashtag tag 3.3, measurable results, and transformative impact on Cobol learning. Okay, this all sounds incredibly well thought out, deeply rooted in cognitive science, and the platform seems amazing. But theory is one thing. Here's where the rubber really meets the road. What are the actual measurable results? When you apply this Pacta CODEX method using this platform to something as traditionally challenging as learning Cobol, what happens? Do these concepts actually translate into real-world impact? Can you quantify the difference?
Absolutely. And the neurocognitive and performance metrics we've been able to collect are, frankly, quite astounding. They really demonstrate a profound transformative impact, far beyond what we typically see with conventional training approaches.
Okay, hit me with some numbers. What are you seeing?
Well, first off, a remarkable reduced learning time. We're consistently seeing around a 65% reduction in the time it takes learners to reach proficiency compared to traditional boot camp or classroom methods for Cobol.
65% faster.
65% faster. What that translates to practically is learners achieving basic Cobol mastery, understanding the core syntax, structure, and common verbs in about 3 weeks, versus what typically takes closer to 3 months. And achieving full development autonomy, being able to tackle moderately complex tasks independently in around 2 months, compared to maybe 6 months or more with older methods.
Wow, okay. That's not just a minor tweak. That feels like a paradigm shift in terms of speed.
Yeah.
But the skeptic in me immediately asks, does faster learning lead to faster forgetting? What about long-term retention? Is the knowledge actually sticking?
That's a crucial question, and it's where Codex truly differentiates itself. The results on long-term retention are perhaps even more impressive. We're measuring retention rates of around 85% 6 months after the initial training.
85% after 6 months. How does that compare?
That dramatically outperforms the typical 30-35% retention rates often observed with classic, more passive learning methods over that same time frame. So this isn't just about speed, it's about deeply embedding the knowledge into long-term memory in a durable way.
Okay, that's huge. And what about applying it? Especially for Cobol, where maintenance is key, can they actually use these skills on real, messy legacy code?
Yes, the skill transfer metrics are incredibly strong. We're seeing about a 90% successful transfer rate of skills learned in the program to the practical tasks of maintaining complex, existing legacy Cobol code bases. This is critical because, as we discuss, that's the bread and butter of so much professional Cobol work. It shows the skills aren't just academic, they're immediately applicable and transferable to the real-world challenges developers face.
90% transfer to legacy code. That's impressive. And you mentioned a fascinating metric earlier about learners being able to actually teach the concepts to others. What does that signify?
Right, the teaching capacity metric. We found that approximately 78% of learners who complete the program feel capable and are demonstrably able to teach the Cobol concepts they learn to their colleagues.
70% can teach it.
This is a really powerful indicator of true mastery. It aligns perfectly with the Feynman technique principle. It means they've not only internalized the material deeply enough for their own use, but they can also articulate it, structure it, and explain it effectively to someone else. That demonstrates a profound conceptual understanding that goes far beyond simple recall or replication.
Okay, so the performance metrics are stellar. But what about the learner experience itself? Because we started this whole conversation talking about the frustration of tutorial hell. How do learners actually feel going through this more demanding active process?
That's a vital aspect of the success, and the results are very positive there, too. We've recorded approximately an 80% reduction in self-reported learning anxiety compared to previous learning experiences, and concurrently, about a 150% increase in reported intrinsic motivation. Learners actually find the process engaging and rewarding.
Less anxiety, more motivation. That's a winning combo.
Yeah.
It really is. It points to a learning experience that, while challenging, is perceived as fair, effective, and ultimately much less frustrating. And perhaps the most telling statistic reflecting this positive engagement is the completion rate.
Ah, yes, the Achilles heel of online learning.
Exactly. For the Pacta CODEX Cobol program, the completion rate stands at an extraordinary 92%.
92%.
92%, which, as you know, is vastly higher than the completion rates for typical MOOCs or online courses, which often struggle to get above 20%, sometimes even lower. This sustained engagement, keeping 9 out of 10 learners actively participating through to the end of a rigorous program, is a direct testament to the method's design. It manages to make learning complex Cobol concepts genuinely effective and enjoyable enough to keep people invested.
These numbers are incredibly compelling. It really paints a picture of learning that's not just about ticking boxes or getting through a course. It's about genuine cognitive engagement, deep learning, and developing lasting transferable understanding. And we've even heard some powerful anecdotes from learners themselves, haven't we? I remember reading about Marie D., a senior developer.
Yes, her feedback was striking. She said something like, "After 15 years actively avoiding Cobol, I finally understood its fundamental logic in just 3 weeks using this method. Pacta CODEX transforms learning from a chore into an intellectual adventure."
An intellectual adventure. I love that. And there was Thomas K., who mentioned having ADHD.
Right. He was a career changer, and he noted, "The micro-content, the short, focused modules, perfectly respected my ADHD. For the first time ever, I could learn a complex language like Cobol without constant frustration." These aren't just technical gains we're talking about. For some learners, it represents a significant personal transformation in their relationship with learning itself.
Absolutely. It's hitting on multiple levels.
And that's the heart of it, really. These metrics, these testimonials, they aren't just about slightly improved grades or faster completion times. They demonstrate fundamental shifts in cognitive engagement, in robust long-term memory consolidation, and in genuine, practical skill transfer. This is the definition of true expertise being built. These are deep neurocompatible changes in how the brain acquires, processes, and applies complex programming knowledge. And the success with Cobol proves this is achievable, even for domains often perceived as uniquely challenging or legacy. #tag outro.
So after this really fascinating deep dive today, it's incredibly clear that the Pacta CODEX method, with its unique CODEX cycle, conceptualize, operate, debug, explain, explore, is truly doing something revolutionary in how we approach programming education. It's designed as a deliberate anti-tutorial, isn't it? Meticulously crafted to move you, the learner, from that passive consumption mode into active creation, active problem solving. From getting that core idea clearly, conceptualize, to immediately getting your hands dirty, operate, then learning to systematically fix your inevitable errors, debug, forcing yourself to articulate your understanding, explain, and finally making sure you can apply it flexibly in new situations, explore. It really feels like a holistic journey towards genuine mastery.
It's designed to be exactly that.
And this whole method, born from Alain STEVENS' really unique background and insights, drawing inspiration from structured knowledge management and law, it really seems to offer a powerful, practical antidote to that frustrating tutorial hell we started with. It does it by actively engineering that crucial transition from just having declarative knowledge, the facts, to building robust, usable procedural skill, the know-how.
Exactly right. And what this all demonstrates, I think, when we connect it back to the bigger picture, is a powerful testament to a core idea. That truly effective learning isn't just about having access to information. We're drowning in information today. It's fundamentally about designing a learning environment, a system that profoundly respects and actively optimizes the brain's natural, evolved mechanisms for acquiring complex skills. The astounding success we're seeing with Cobol, a language often dismissed as uniquely challenging, maybe even arcane, powerfully validates this entire approach.
It proves the model works, even on hard problems.
It proves the model works. It sets, I believe, a new potential standard for how we should think about training in any complex skill, not just programming. It shows that by carefully aligning our pedagogy, our teaching methods, with what we know from neuroscience about how learning actually happens, even the most challenging domains can be mastered efficiently, effectively, and remarkably, even enjoyably.
So, thinking about all this, what does it all mean for you, our listener, as you go about your own learning, whether it's coding or something else entirely? Next time you find yourself tackling a new skill, maybe trying to learn a new programming language, or perhaps mastering a musical instrument, or even learning a complex craft, maybe pause and remember this Codex framework.
Instead of just passively consuming another video or book, maybe ask yourself, how can I deliberately conceptualize the absolute core idea here with maximum clarity and minimum fuss? How can I immediately operate on it, get my hands dirty right away? How will I structure my approach to debug my inevitable mistakes and learn from them systematically? How can I force myself to explain this concept in my own words to really solidify my understanding? And crucially, how can I actively explore this new knowledge in fresh, varied context to ensure I build true mastery and transferability, rather than just getting stuck in yet another tutorial hell loop?
That's the challenge, isn't it? In today's world, utterly inundated with easily accessible information, the real competitive advantage, the real key to progress, lies not just in what you know, but increasingly in your ability to effectively learn new things and transfer that knowledge to solve novel problems. The Pacta CODEX method, as we've seen with Cobol, isn't ultimately just about learning Cobol better. It's a potential blueprint for mastering any complex skill by engaging your brain actively, systematically, and in the precise ways it's actually designed to learn best. So the final provocative thought we'd leave you with is this: what complex skill will you decide to codex next?